And that's crucial to solving this problem here. So what I decided to do here was basically stare at this and make a nice observation. And to be honest, maybe I'm not quite cheating, but kind of maybe doing the opposite and illustrating why it pays to know some additional mathematics beyond the A-level syllabus. So I actually did this using modular arithmetic. So I noticed here that this number, mod 4, was 0. So this number here, without using modular arithmetic terms, is just always going to be a multiple of 4. Firstly, how do I know that? Well, the reason being is because n times n minus 1, those are consecutive integers. So one of them's got to be odd, one of them's got to be even. So I'm doing an odd times an even number, that's going to be even. And then of course I've got this 2 in the front, so an even number times 2 makes it a multiple of 4. And you might go, well, great, that's amazing. Why is that at all useful? Well, the idea is, well, if I look at 3 to the n, if I think about powers of 3, there's only 2 possible values they can be mod 4. So again, using non-modular arithmetic terms, if I look at the powers of 3 to the n, in terms of the remainder that they give when I divide by 4, there's only 2 possible values they can give. So if I just look at the first few powers, 3 to the 1, 3 squared, 3 cubed, 3 to the 4, and so on, this is 3, this is 9, this is 27, this is 81. And if I divide them by 4, this gives me remainder 3. This gives me remainder 1, because 9 divided by 4 is 2 remainder 1. This gives me, remainder 3. This gives me remainder 1. And it will go 3, 1, 3, 1, 3, 1, and so on. And very, very nicely, this is purely dependent on whether the power of 3 is odd or even. And that's crucial to solving this problem here.